Okay, thank you. My 30-second rule was, like you don't watch the first 30 seconds of any talk because it's like nothing interesting, so you just skip the first 30 seconds and you're still good, you have the talk. My rule was to make the 30 seconds the most interesting of the talk by starting with a bang, but all this microphone thing kind of messed that up, so there goes the plan. I'm going to talk about, just change the title a bit, because, yeah, kind of unexpectedly successful, whatever. So I'm going to tell you 3 stories related to the D language that I think are just very interesting. To wit, I have like, kind of half a dozen folks in the audience, which is awesome by this conference's standard. This is not a languages conference. I'm very happy you came. I hope nobody's going to leave before. It's like, oh, I can't put up with this anymore. So I'm going to give a bit of introduction in what the D programming language is all about, and then I'm going to give you like a few anecdotes about it that I think are just interesting in general, not related to the D language in particular, or even to any language. They're kind of, telling about programmer psychology. So let me bring to your attention a company called the Red Telephone Company. And it was a company developing itself in Australia in the 60s and 70s. And they had this their typical phone was literally red, and they had going, and they had a brand. It was a nice company, and they would do good business there until some regulation changed. And the way the regulation changed was the competition and sort of the way the phone regulation worked at that time imposed that there is a constant cost per talk, not per minute. So you would, as a subscriber to a phone company, you would pay the same amount of money whether you talk for a minute or 10 or half an hour. Okay? So that was a problem for their particular cost model, which was they would pay the provider of cable or whatever, they would pay by the minute. So the year was like 1971, and they were looking desperately for a solution to that problem. And, how do we make our customers talk less? Which is kind of an interesting problem to think about because, what would you do? Like, ideas, please, from the vast audience in this room. Yes? Sorry? Break the call, and then, of course, you're going to have the risk of losing customers if you kept on doing that. So that was not a very good solution, but definitely it's one of the things you may think about as a possible solution. What other ideas do you guys? Yes? Make the phone call what? Oh, yeah, so kind of make the phone call of poor quality so people get tired of that. So that's actually very interesting. It's very telling that you came up with this idea because it's actually related to what they ended up doing. So they brought a consultant, and the guy said, you know what? Make the phone, the handset, heavier. So they put like a piece of lead in the handset. I'm not kidding. So they made the handset heavier, and people would talk for a while, and they're like, you know what, I'm tired. I'll talk to you tomorrow. Right, because it's just starting to hold. So that was very successful and kind of prolonged the lifetime of that company, and then it was acquired, et cetera, et cetera. But it was a very nice idea coming from a completely unexpected angle and ultimately realizing the goal. So my purpose here is to tell you 3 similar stories. And, my hope is that by the end of this talk, you're going to be like, oh, yeah, so that was kind of an interesting segue into these 3 stories. Awesome. So let me talk a bit about in a general sense. So systems-level programming are still a necessity. There's quite a few application categories with what people call, if I were an economist, I would say elastic demand for performance. So what does it mean, elastic demand for performance? Who knows? Who's been doing economics in college? I don't know, nobody. Okay, great. I'm very happy. Me neither, but I happen to know this term, which is elastic demand means the more you have, the more you want, right? Like, you know, to some extent, what can you think of that has elastic demand? Drugs. Awesome. That's a good one. So I hope the camera is not going to see who that guy was. But something of more of a staple that would have an elastic demand. To some extent, actually, food, kind of the big food companies have shown that the demand for food is a bit elastic in the sense that they keep on increasing those Coca-Cola cups, right? But for example, taxi rides. The cheaper it gets, the more you ride, and that's Uber. Like Uber was successful because they figured that out. It's amazing. So they figured out people are not going to stop using cabs if they get less and less expensive. They're going to use more and more cabs, which is amazing. Now, there are quite a few domains in our realm, in computing, where the demand for performance is elastic. Can you give me examples? Sean. Photoshop, thank you very much. Genius, yes, I bow to you. So, of course, in Photoshop, you have tasks, you mentioned there's one particular task that took 8 minutes to complete. And in all likelihood, there was an iteration going on. So people wanted to continue doing other things after the 8 minutes have passed. So if you reduce those 8 minutes to 6, 4, or 2, that would be a very significant increase of productivity. So and there's actually literally no limit to how much you want to crank up that computation, because then you get to do a lot more things with Photoshop. Other applications. Other domains in which there's not enough power, graphics, yes. So that would be related. Yes. Animation, what have you, yes. I mean, yes. Broadband. The more you get, the more you want, definitely. And actually, there may be a saturation point. I'm thinking to make resolution, 5K, how much more do you want? So probably there's kind of an eye limit there. But then you want low latency, so yeah, indeed. But there will be more money-making kind of alternate kind of things. Oh, come on. Huh? Memory? No, but in computing, what algorithms, what kind of domains of computing, what applications of computers have this elastic demand for performance? I was saying money-making. Trading, money, market analysis. I mean, here's the thing. When the market closes, a lot of companies have until the open of the market next day to crunch numbers. And the more numbers you get to crunch, the better models you have. And it's like the relationship is clear. There's no limit to how much you can do. There'll be a lot of other applications, such as pretty much any, compilation speed. If you use C++, there's no limit to how much speed you want in compilation because it's so terrible to start with. All right, so then we have this one tendency is we have systems level programming is still necessary because of this elastic performance demand. And then we have ever-growing modeling needs. So we don't want only fast applications. We also want larger and more complex applications to develop. And for a language that is systems, you want to kind of keep all in the same language as opposed to straddling across multiple languages. And the alternatives to D are missing for one or more of fast compilation, fast generated code, which is a completely different matter. Modularity of code, expressive power, enabling paradigms, and safety. So if you look at the landscape of systems programming languages, or programming languages in general, you're going to find that some are going to fulfill some of these points, but not others. For example, a common friend, C++, which of these it doesn't quite fulfill? And which does it very well at? Fast compilation? I'm seeing nopes. Speed of generated code? Awesome. Really nice, right? So here's modularity. I'm kind of translating for the camera, the body language I'm getting from the vast audience here. So modularity has like a number of things to it. One of them being like the compilation model is against modularity for the, that pound include model, which kind of exposes everything, and this white boxing of files and that kind of stuff. So, there's multiple aspects to modularity, and C++ has quite a few issues there. Expressive powers and enabled paradigms, C++, pretty good, not bad at all, compared to like a lot of the competition. Safety, you're being very nice there. I mean, come on, right? You're being super nice. Okay, so, all right. So there are other languages such as Rust, which comes from the safety angle, but kind of the fast compilation expressive power kind of just squeaks out. All right, great. So we're looking with D for a language that would kind of light up these fundamental requirements. And my personal story goes the following way. As some of you may know, I'm a big kind of C++ pundit from years back, and I've been coming from that angle. So I was very happy that C++ has good modeling capabilities, has an efficient underpinning. Very nice. Again, the whole C memory model and kind of paradigm is very nice. The problem I kind of found, like, for example, the meta programming C++, even though it does things that at the time were like pretty awesome, it's very arcane. For example, there's no if during compilation. And I mean, picture this. You're using any language, and they say whenever you need an if, you need to call a different function. You would say, please don't do this to me because I have a life to tend to. So no, you don't want that. You don't want to recurse or overload or kind of go somewhere else whenever you need to do a branch in your program. Like if is sort of the most basic thing you may want as a facility in a language. Unfortunately for compile time C++, there is no such thing. And this led to a phenomenon because of the arcana involved in doing metaprogramming in C++. It led to this like not user serviceable libraries, such as good portions of the Boost library, which are like, essentially inscrutable from a user perspective. You have no idea. I've had quite a few experiences with Boost where I'm like, where is work being? So I'm having a problem. I want to look at the source code to see where how hard can it be? How difficult can it be to say, I'm using this library, it has the source available, all I need to do is look where in the source the work is being done so I can figure out what's happening. Well, yeah, I'm saying this, oh my God, so I'm kind of, again, I'm doing for the camera unsuccessfully your beautiful face here. And there's this whole, what's the word, like scaffolding in Boost that you look at and you go through and you have no idea where the work is being done because the lines of code that actually do work are very few by sheer numbers, as a fraction of the total code, because it's all like redirection and templates and all that stuff. So I didn't like that. I didn't like that C++ has poor introspection, which I think introspection is one of the fundamental things that allow you to write good and fast software. Introspection meaning you have like code and you get to actually inspect the code and see what are your methods. You look at the class, say what are your methods, enumerate the methods for me please, so I can see them by name and what arguments they take, etc. And all of this should be done during compilation so you can use the object. Hey Phil. So and the compilation model is impractical. We have a whole team at Facebook, which I was a part of for a while, which, it was a full team of good engineers and me, plus me, right, who had as their only task, like, make builds work in C++. It was a parallel system, thousands of machines dedicated to making all the engineers at Facebook write C++ code and build it fast. It had a lot of caching going on. There's a lot of engineering that went into that parallel build system simply because the model of compilation you start with in C++ is bankrupt. It's terrible. Actually, it's an amazing feat of technology that Hello World works. And so many things happen. If you just pre-process Hello World, do you know how many lines you get? Huh? 90,000, depends on, like, I got 57,000 with Clang, which is awesome. It's very little. But it's like a 5-liner. And you look at the compiler has to rummage through tens of thousands of lines, megabytes of code to get to the point where actually generates an object file and then, an arcane format to itself. That's a kind of a whole different problem. And then it gets linked with another arcane format, and then it gets into executable that actually works. The fact that that whole pipeline even works is an amazing feat of engineering. Congratulations. We're amazing. I mean, the sheer fact that we got this to work is fantastic. All right, so, okay. And then I kind of concluded as a corollary to these issues I was having, I was trying to express these difficult metaprograms in C++. And I figured out actually what I'm getting is modest results with disproportionate effort. So there's kind of this, this misalignment between what you put in it and what you get. So I was not happy with that. So I said, let me actually try this other language and work on it and improve it. So the principles of D are, we want to leave no room below, so you don't need to escape into a different language to do performance work, which makes sense. It's multi-paradigm and balanced. It's practical and principled and avoids arcana. And why would you want to look at it? Well, the party line is 3 things: convenience, modeling, power, and efficiency, which, again, are difficult to find together. They're easy to find. Like 2 of them are easy to find in other languages. The actual reasons I've been discussing with people are, actually, what I like is that it compiles quickly and produces fast binaries. So that was one thing that a lot of people appreciate. It's easier to get into than other languages. And it's fun to work in. So the fun factor is definitely there. So it's not something negligible. So, the fact that a language is fun to work with is definitely a good sign. Why not? Why don't you want to get, every language proponent has got to have the slide. If a programming language has only pluses and or minuses, that's a lie. That can't be, right? So definitely there's minuses. There's no party line to why you shouldn't use D, right? That's why I left an empty bullet there, right? The actual reasons I heard from people was actually D is poor on formal specification. It's unclear, it's not very well defined. There's little corporate pickup and support. There are only a handful of large companies using D at the moment, along with larger, but not huge, sort of grassroots community. I would estimate that the user base of these couple of orders of magnitude behind the likes of Java, C, and C++, which is still a lot of folks, but it's not as huge as the consecrated languages. Not many libraries, and it's a large language to learn. Now, first anecdote. From turtles to dependency carrying code. All right, who knows the joke with the turtles? Turtles all the way down. Tell it to us. Actually, I'm going to tell you because I have the microphone. It's difficult, yeah. So the way it goes, I would need to repeat everything you say. So the joke goes, a scientist gives a talk, a physicist, right, gives a talk at a kind of a layman audience and gives a talk about universe and physics and, kind of planets, whatever, kind of big things, astronomy, whatnot. And at the end of the talk, there's this old lady coming to him and says, "Oh, you're all wrong, young man. You got it wrong. The whole universe sits on a turtle, on the back of a turtle." And the guy says, "Oh, okay, so I have a fun conversation ahead of me," the scientist thinks. So he says, "Well, what's that turtle sitting on?" "Oh, it's another turtle." And the guy says, "How about the other turtle?" And the old lady says, "You're trying to fool me, young man. It's turtles all the way down." So she had this nice infinite regression going on in her mind. So that's the story with the turtles all going all down is a good example of what's called infinite regression in science. And it's one of those things that kind of go like fractally all the way down. And I'm going to show you an example of using this principle in programming language design. And I'm going to take that to dependency carrying code, and I'm going to define that. So let's start with hello world. Okay. So hello world has, I put like a scripting line there, so you can actually use it, run it like a script with a shebang line and everything. Very nice. It has an import, which is, you can imagine, it's like pretty much like in Python, or like pound include in C++, or what have you, or in Java and any other, C#, whatever. And we have a program that's void main, and it does a write line. And that's pretty much the program. And well, there is a few questions. Why didn't you import for everything? Why don't I have just a one-liner that does it all for me? There are answers to that. But I don't want to focus on that. I want to focus on something different, which is a slight change to this program, which goes this way. What is the change? I push the import inside the main function. So I kind of made like kind of a sort of a file inclusion or whatever, library, whatever the hell lookup thing. I put the library use inside the place where it's used, which is odd. I mean, if you do this in C, a kind of a pound include inside a function, it may actually almost work. But you would not be up for promotion after the next review cycle at your employer. This is not going to push your career forward, my friends, right? It's pound include inside a function is a no-no in C. And in C++, it gets even weirder. In C, it actually can make a lot of things work if you pound include inside a function, among which structs are non-local. Can you define a struct inside a scope in C? You can, but not in C++ because you count it's different. It's the whole. Huh? Yeah, you can, but there are different semantics, what I'm saying, right, as opposed to, because usually when you include something, you include for linking purposes, so then the whole symbol mangling is going to be different. You can use local classes and templates. All right. Awesome. Now, in Python, actually, there's a discussion going on about the merits and demerits of doing this in Python, which is undecided at this point, my understanding is. And in Java and C#, it just straight doesn't work, right? So now, the fact that I'm putting the import inside the scope is I want to do anything everywhere. And that's the way of the D language is you put anything anywhere in D. You can actually put functions instead functions, types inside functions. You can put generics. You can put whatever you want inside everywhere else. And that's infinite regression because you get to put like in any scope, no matter how deep down it goes, you can still put anything in there. And that's a nice design principle, this fractality of language constructs, but it didn't apply for import. And one morning I sat down and I did this and I tried it and it didn't compile. So I called Walter Bright, the inventor of the D language, and I said, Walter, I tried this and it doesn't work. And he said, let me look through the compiler source. Says, well, the first line in the compiler source is when you type check import, you check that it's at the global level. Otherwise, it's just an error. It just aborts compilation. And I said, well, why don't you comment that check out and see what happens? So he commented out, and the rest, essentially it worked. So we got it working like it was a removal of a limitation that what made things work, as opposed to consciously designing a new feature. So remove the limitation, it worked. Then we had, we did some more work with type lookup, with the name lookup and stuff to make things proper. So it just worked. So that was it. How big a deal do you think this is? Is it big or is it small? It looked like a small deal. All right. So, and then we said, well, how about you put imports in structs and classes, and wherever you have a scope, you can put an import. That should be natural, and it is. So that goes for those two. And it got to a very interesting point where you can say, actually, the definition, the import is actually a dependency, is what makes this particular widget or function or whatever work. Is it's conditioned by the existence of that particular import. It doesn't have to be a standard import. It can import any other library that you may have or may not have. So that means the definition of widget here is carrying its own dependencies. And if you move it around, the dependencies are going to go with it. which is fascinating because this is not traditional. Traditionally, people think of dependencies. This file depends on this file, and that's how make works. And that's how all the tools like make work, right? It's like, oh, I have this file, and what are the dependencies of this file? Oh, it's like these other files, and these other files in turn depend on these other files. But actually, with this, you get to completely change that, put it on its head, and say, actually, it's not the file that depends on the file. It's a definition inside the file that depends on a different library file. So, that's kind of weird. So, in all likelihood, there's consequences to that, and indeed there are, when you get into templates. So now we have a template called function log, like not mathematical log, but I'm talking about logging something to a console or whatever. So I'm going to write a generic function called log, which takes 2 sets of parentheses, and that's how you define a template function in D. It's much more concise than in C++ with the template keyword. So you say the first round of parentheses are like my compile time parameters, and the second is like my classic runtime parameter. So I'm taking any type T, and I'm taking one value of that any type T. So, okay, fine. Inside the log, I'm going to import these guys, and I'm going to do whatever, I'm going to write the current time, and I'm going to write some stuff, and I'm going to call log within the file, within main. Fine. Now, the question is, for everybody of the vast audience in this room, if I comment out the call to log, should I even look up those particular libraries that log is using? I shouldn't, right? I'm seeing negative nods here. Indeed, there should be no business if I'm not actually falling the tree in the forest, if I'm not cutting the tree, if I'm not using the function log. That's a pun, log, right? Trees. Come on, you guys, come on. What's happening there? Huh? Yeah, joke hand. Yeah, I gotta get my joke hand going there. So if I comment out the call to log, it means the dependencies are not even realized. They're not looked up. Those files could be missing, is what I'm saying. Which is very awesome because, hey, at this point, I get to this point where I'm like, oh, okay, so what I could do is deploy a large library of artifacts, each of which has its own dependency, whatever it is, whatever necessities I have. But it's pay as you go. If I use nothing of that library to start with, I pay nothing because I'm just paying the parsing of that particular code, which is nothing. Like in the economy of a build, parsing of the D code is like nothing. It's actually nothing in C++. C++ parsing with improvements in technology has gotten to the point where it's very low cost. Even though traditionally it was very high. So now we have this nice setup in which I deploy libraries. I don't think of file dependencies and stuff. All my focus is I'm going to give you the generic components and you instantiate whatever you want. And at that point, the dependencies will be realized, meaning the files are going to be looked up and imported, which is where the big cost is. Very interesting. Of course, with a bit of engineering, you get to kind of, once you actually open an imported file, you cache it, so you don't need to open it twice in 2 different functions, yes? Like if you import like that std date time in 2 different functions and instantiate both, of course, you don't want to open the whole file again and parse it again and everything. You just cache it. And that's trivial engineering. So now we have like generics that are faster to build and import, and which leads to an interesting thing, which is less pressure on the linker, which goes the following way. Who knows how a linker works? Sean, there should be nobody, because you have a life to live, right? You should not know how a linker works. I'm really sorry for you and myself that we know a bit, right? Because it's like kind of this, right? So, a little. So let's see, what does the linking process look like? So you have object files and you have library files. How does it go? You have a bunch of tables. Right, so but the point being that with the object files, whatever symbols get resolved inside the object file, that's a quick process because it's there, right? It's in memory. But when you, whatever unresolved symbols you get, those remain for the second step, which is looking at in other tables which are archived. There's an archive format for libraries, and there are many object files kind of collapsed together, and you kind of look up, load a bunch of files, large files, and look up those tables and stuff, and so on and so forth. That is the long part of the link process. That is why linking takes a long time, because you have these large files to consult. If you get to resolve most of your symbols within your object file, you're good. And guess what? With this model of compilation, that's what you get to do. You get to resolve a bunch of your symbols immediately. And it costs you more to compile those functions, but it takes you less to link. And it turns out, guess which is faster than the other, right? So compilation have a bunch more control of, and you can actually make it a lot faster. So that's less pressure on the linker to essentially less time spent linking code and more time compiling code, which is a good trade-off to make. So we got to this point that is completely weird, because we started with something completely innocent, which is like, I want to put an import inside the scope. And it was a very, one of those nicey things to do, and it led us to some unexpected point. But wait, there's more. I can measure what happened if you take a large library and convert it to this approach. And there's one obvious large library in the D language, which is its own standard library. So a lot of people have done a lot of work in converting the standard library to the new format, which everybody now recognizes is superior. I'm sorry for bothering with the camera there, but I got to walk here because I think this is very interesting. So that led to the reduction of 4.45 times in the speed of importing a library. So just you type import, you do nothing else, and it just accelerated. So it got down to 64 milliseconds, which is next to negligible. And even better, it got, when you do this kind of dependency carrying code, it got to actually smaller object files. Because when you import the library, it's going to get its static initialization. Yes, you know, libraries have like these. You need to initialize some things in some libraries, and it leads you to additional code that you need to build in. And it leads you to more dependencies being realized, and it leads to kind of an avalanche of other things. And guess what? You get to reduce the object file size because dependencies are on demand only, not compulsive. So you got to reduce the object file size as well. And of course, that means faster linking and everything. So that's actually a pretty hard measurement of something that looked very wishy-washy in the beginning. So that's pretty awesome. So the consequences now are that we have definitions that carry their own dependencies to them. That means refactoring is a lot easier because you get to move the code wherever you want in the application without worrying, oh, I need to go to the top and pluck those imports as well. Yes? Now you have you get to do physical design, meaning layout of files, any way you want. You don't have dependency constraints anymore. They're all automatic. It's just by yes. Does it mean we're going to have runtime exceptions if the dependency is not is incorrect? No, you're going to have compilation time, kind of instantiation time, which is during compilation exceptions. For example, if you use log and the dependency is not there, for example, it's missing a file or whatever, you try to build, it's not going to build. So it's not going to be delayed all the way through runtime. But if you're, imagine my point here is that log function could be one of thousands of functions in a large library, right? And if you use you don't use all thousands of functions, you use 5, right? And only dependencies for those 5 that you actually use are going to be executed, tried, instantiated. So that is where you win. You win during build time, it's not a runtime issue. Great. So now I have this pay-as-you-go paradigm, and it led to fast and scalable builds for large projects. Because it turns out that it's a very common pattern in projects to import a whole library, use a small part of it. And then you have a different module, imports the whole large library, it uses another part of it, and so on. And that's the way the cookie crumbles. And then you just get this pay-as-you-go structure for large projects, which is amazingly efficient. You're looking at orders of magnitude in the limit improvements of build speed, which is awesome. So we had this heavy handset effect. Remember the red telephone company story? We have this weird consequence, which is the heavy, shorter call times. Natural lexical scoping leads to faster builds and small object files, which is highly surprising. Great. Story number 2. Big laugh. This brought down the house, this like immaculate conception thing. And it's like, oh my God, this is so funny. I can't stand myself. All right. So what do I mean by that? Well, let's recall the definition of a pure function. Pure function. Like, Haskell, right? Functional programming. What is a pure function? Doesn't have any side defects. Thank you. So a pure function is like produces the same output from the same input now or whenever. It's independent of typical examples of pure functions. Sorry? All of math, sine, cosine, log, x, what have you. Although that's not entirely true because some set there, no. That's ridiculous. But anyhow, so in general, like pure math does not. What else? Printf. No, printf prints to the screen. You can't. It's going to do a different thing. So, toString, yes. It produces the same string from the same sprintf, yes, sprintf would be. Okay, printf would be the sort of the antithesis of a pure function because it does something every time you call it and it puts in a different place or whatever. Great. So, my thesis is the following. It is difficult to write a whole program in a pure manner. It requires advanced understanding of type systems such as monads and things like that. And so it's kind of a difficult thing. However, I sustain that if you get to write fragments of programs in pure style, this is easy and useful. Because it allows you to very easily analyze and understand those pure functions, much easier than if they were kind of part of a big mess that was like all globals and all crap. So that's my thesis here. And, to add a nice effect here, pure functions generate better code because, for example, the same pure function called twice, you get to do what? There's a keyword here, memoize. Yes, right? Memoize. You get to memoize the function because you know it's going to return the same result every time. So if you call it the 2 times with the same argument, you just remember the first call and you're done. So, all right, the problem is how do you interface pure with impure code because they work very differently. All right, so let's take an example here. We have a functional factorial. So if you actually, I'm going to try this stunt right now. All right. Where's my cursor? Okay. I've never done this, okay? Functional programming examples. Which are the top 3 results, you think? Quicksort? Factorial, which is the one we're discussing, and? Factorial again, and there's one different one. Huh? Binary search, maybe not. But I bet you that within the first page we're going to see Fibonacci. All right, let's see. All right, this should be fun. All right, so functional programming, a practical introduction, functional programming by example. All right. Okay, this is kind of a long chapter. All right, let's go to the Wikipedia page here. And let's see, let's go down to an example here, history, recursion. All right, length. Type systems, data structures, oh, come on, okay. Printing first 10 Fibonacci numbers, iterative, printing first function expression style. All right, very nice. All right. Fibonacci again. Come on, something else. Oh, it's the same Fibonacci all over. Like, Oh, D. Oh, there you go. Somebody introduced that as well. So, okay. Let me try the second hit here. I don't know. What is this? Factorial Programming Basics. Squint. Okay, this is not an example. Squares of. Okay, awesome. Okay, this goes on to show if you try something like this, kind of going online in the middle of your talk and try to prove something is never going to work. So we have the Fibonacci, we have the increment. Come on. Squares, range, people, height. Oh, come on, man. This is incredible. Functional programming examples. Examples. Oh, okay, that should be interesting. But I suppose these are rather advanced. Reduce. Okay, awesome. Well, I'm going to declare this as a qualified failure because my hope was within the first page I'm going to see Factorial, Fibonacci, and Quicksort, all of which are computationally problematic. So they're not. To wit, this is not the way to do Factorial functionally. This is the wrong way of doing it. And that comes with sort of the advanced, like, okay, here's how you do Fibonacci recursively nicely. But actually, this is not the right way of doing it. What do you think is bad about this particular function? Well, it's what they call p-space. It takes space proportional to the input because in order to actually compute the factorial, you need to compute all of the previous values and have them as temporaries. The problem being, I need to compute factorial and then I need to compute the multiplication and only then I have access to the result. So it's going to take me space proportional to the input and that's not efficient. It's not computationally smart. It's not the right thing to do. So that's terrible. However, the nice thing about it is pure because it doesn't change any variable. It doesn't use any assignment or anything. It just computes the thing and it goes. So it's pure. So notice I put like the pure attribute there onto it, which is great. The way it's actually taught, like the right way of doing factorial is to use a helper function, which I call conveniently crutch. Like it's a helper which is going to actually thread the temporary result through the computation in such a way that it allows me to use what's called tail recursion and therefore get rid of the space cost. So the way this works is I'm going to start crutch with n and 1, which is my first intermediate result, and then I'm passing that into the function, and then crutch is going to recurse to itself with n minus 1. Now, the question for you is, what is the difference between crutch and this approach and the previous approach that makes this more efficient and desirable? Yes? Tail recursive. Why is it tail recursive? How can you tell?
Because you are either returning a direct result or the result of a recursive call. You do not need to store previous parameters.
Right. So thank you. So how you identify these cases is that a function ends up with a call to itself or a final result. It doesn't end up with a call to itself plus some more computation, like here, because here it calls itself factorial n minus 1, but it needs to do multiplication after it knows the result of factorial, and that spoils the whole party. So, all right, so you know what? This is not how it's defined in the math manual. In the math manual, it's defined with a big pi. Right? It says pi from I equals 1 to n of I. It's a product. It's an iteration. It's not in math, they don't teach you this. Then they say, oh, if you're really among the smarter students, you're going to get to do this. Which I think is ridiculous because, as a student, I want to see like the math and I want to see the mapping of the math in software. So I want to actually see an iteration. And this is how, this is the iteration. It's a product of all numbers between 2 and n, right? So that's what it should look like, but it's not pure. because it changes the result during the working of the function. It changes the result iteratively many times until it gets it, and then. But that's not pure because it has, it kind of has assignment. It has this star equal I, which destroys the whole mood here, right? Well, now you know what? I got to a point in my life where I got to question everything. You know, I'm saying, you know what? I'm not going to accept any of these preconceived notions of purity and things and whatnot. So therefore, allow me to retort. What does a pure function look like? Cultural reference? Yes, you get it, you know. Oh, come on, you guys, you're too young. Pulp Fiction, the movie to watch. Okay, after this homework, you got to go and watch it, okay? All right, by the way, we have like 12 minutes. 12 minutes to go? Thank you. All right, so what does a pure function look like? I mean, what is pure really? Well, we said pure functions always return the same result for the same argument, which is sort of the teleological, the purpose-oriented definition of purity. Is not the implementation-minded version. It's like you shouldn't modify globals because otherwise, you know, the big boohoo is going to come and get you, right? It's not that. You should think of it in terms of effects. Pure functions always return the same result for the same inputs. Nice. That means you shouldn't read and write global variables. Global constants are okay. You shouldn't call impure functions. But who said anything about local and transient state inside the function that nobody gets to see? Who said anything about that stuff? Why can't I actually be a little impure in my bedroom? I mean, as long as I appear to the society as a pure, law-abiding, tax-paying citizen, who cares what I'm doing within my own quarters, right? I mean, I'm looking at the vast audience. You're like left and right. Yes, thank you very much. So, I mean, pure is as pure does. It's effect-oriented. It's not implementation. It shouldn't worry about the way implementation goes. And actually, you know, so once we got to this point, in the D language, we had the chance of redefining what pure means. So we said, you know what? Actually, this should be pure. This is a pure function. It does iteration, it does mutation, but that's a private state. By the end, you get to see any effect of any result of the function. The fact that it's implemented with iteration, recursion, crutches, or whatnot is irrelevant. And therefore, I'm going to be able to put pure. So the type checker in the D language has actually a verifier that makes sure that anything you modify is local and private. And you're good because it's, look at the result. It's kind of a local variable. So pretty awesome. All right, let's push this one up. Let's write a function that reverses an array, like std reverse in STL in C++, yes? Reverse an array. And my question to you, this is kind of a classic implementation, but my question to you is, should reversing an array be a pure function or not? No, it shouldn't. Why shouldn't it? It changes state that outside the function is not private. Yes, however, let me ask you this. If I pass the same array to a function 1,000,000 times, is it going to do the reverse? Is it going to do the same thing? If I pass the array Sean parent 1,000,000 times, am I going to get the same result? I can't pronounce it, but it's going to be the same. Like it's deterministic. So we have kind of an interesting concept here, which is how do you define the same inputs? Is it the same pointer? Is it the same address? Or is it the same content of the array? So you actually get to push and relax purity even further and say, actually, this is pure as well, because it has the same effects for the same input. So long as you define the input as the reachable content from the parameters. It does not use any globals. What it does is not influenced by the time you call it, right? So obviously a possibility is to disallow, but actually we experimented with this and we figured that it's amazingly effective to just relax the rule and operate with the transitive closure of state reachable through parameter, which kind of a simple way to put it is whatever you get to starting from A there, the array, is you define as your input. And as long as all you use is the input and no globals, you're good. So this is an interesting superset of purity, and it's all in the signature. So there's no need for other kind of, super pure, weakly pure, whatever. You just put pure there and it's understood. So you get to very interesting points where actually you can implement pure functions for user-defined types, such as big int, which is like an unlimited precision integer in the D language. It's a standard library. So you get to say, oh, I'm defining a factorial for big int, and big int is written properly with the appropriate pure primitives, and then this just works. So that's pretty awesome. And actually, you don't even need to put the pure attribute there by hand, because for a bunch of functions, the pure attribute is deduced instead of being written by the user. We figured that if we ask people to write pure, they're just not going to do it. People, they don't want to put in an investment now for a future possible benefit. So the compiler is the best tool to just do it for you. So very interesting. The aftermath here of purity is like if parameter reach mutable state, then we have this relaxed pure notion, no globals, no input and output, and no impure calls. And if parameters are indeed immutable, then you have like pure, like in Haskell. It's the same thing. So this is very interesting because you can use the relaxed pure functions to implement the strongly pure functions. So that's pretty awesome. This has been a very interesting exercise in kind of questioning the preconceived authority on what pure is and what it is and shouldn't be. And we figured that, as long as it's private and etc. And then we got to the parameter, and it got to combining purity with mutability improves both, because you get to write more elegant implementations of sort of classic pure functions. So suddenly we have this. The last question I'm going to say, in like 5-6 minutes we have left, is stringly generative programming. This joke brought down the house. You know about stringly typed? Yes? In like a number of languages, stringly typed programming as opposed to strongly typed, it's a play on words because they use strings to express types. That was completely useless because you all knew that, right? Apologies. All right. It's for the general audience. I'm sure millions of billions of people are going to watch this, and I'm explaining for the sake of them. So what is generative programming? Code that generates other code. And for my money, this is the most fascinating area of computer science. I would highly recommend you consider looking into this deeply, because there's just a lot of generous, interesting things there. So, all right, so that's generative for you, and the specification of these, this code that generates codes is often presented in what I call what's called a DSL, which is, thank you, domain-specific language. So can you give me examples of domain-specific language, thank you, that you may use on a daily basis? Huh? Gradle, that's a build system, right? Yes, build systems, make, Gradle, and what have you, right? Amazing, CMake, it's all DSLs. What others? Huh? Lexiac, thank you, excellent. SQL, domain-specific language, awesome. And actually, you get to embed sometimes SQL. You have even like in C#, you have this awesome link with a Q, right? Very nice, embedded language. Others? Okay, you didn't tell my favorite, which is regular expressions. Yes, it's a very concise DSL for expressing patterns in strings and stuff, automata and stuff like that. So there's just plenty of it. Even printf is a DSL because you get like the percents and all those weird formatting flags that everybody knows or needs to look up every time they use them. Regular expressions, BNF grammars, Lexeniac, portable expression grammars, a newer thing that is like BNF, SQL. Oh, everybody mentioned this. Like, this is amazing. So now, if you get to express this in your own language, such as Ruby, C++, Perl, or Python, or what have you, you're going to get the same syntax for all of these languages, which is unpleasant. Yes? Here what we want to do is use with their own native grammar, process during compilation, and generate decode which would be comparable with a sort of a static compile time jitting, just-in-time compilation. And let me explain. First of all, a bunch of these usable during compilation, which has been cargo culted into other languages as well. And this is awesome because I get to compile factor of 10 during runtime, or I get to say static here or enum, and in that case it's going to actually run the function in interpretation mode during compilation. And this is very nice because I get to decide when things are done. Yes? It's a very nice artifact that we can, so it has a loop, it has mutation, it has things, and all of these are going to be interpreted. And actually there's a guy in Germany who works on a JIT during compilation, which is going to be like 1,000 times more fast than just interpreting the AST of the function. So, very nice. All right, and then we have like another thing, which I'm going to say is the stringly part. In D, you have this keyword called mixin. And what you get is like an idiot. You get to put a string in it and give it to the compiler to compile it for you. Which sounds ridiculous, right? So the first mixin that I'm saying, mixin write line, and with the escapes and everything, I get to write line hello world, which is nothing of interest. But the second use is more interesting because I get to call a function during compilation. It gives me a string, and I compile that string into machine code. So wait a second. I mean, we can evaluate most any function during compilation, and we can transform any string into code. Wait a minute. I mean, there's something here, right? You have like any function and you have any string, and any function that produces any string you get to make into code. That sounds like ASM.js and script, and you kind of generate a string that's going to be interpreted by the JavaScript compiler, and it's going to be very fast and very nice. And so something similar is going on here. And all of a sudden, it opens you the door for a bunch of generative libraries, such as bitfields, which are not present in D, but are present in C and C++. And with this way, bitfields, like that bank syntax is instantiated a template, which in turn is going to generate a string, which is going to be compiled by the compiler. And I'm giving to bitfields, I'm giving, please lay me out a uint called x of 2 bits long, an int called y, 3 bits long, an int z, and so on and so forth. And the mixin is a user-level function, not a compiler trick. It's a user-level function that's going to generate me, guess what? Strings for all of that shifting and masking that's needed for doing all that bitwise work. And then I'm saying mixin here is generating me the string I compile, and I get code that I use like regular code. So, okay, so that's a good start. Pretty awesome. Well, and there comes a guy who wrote a whole parser like that. Thank you. So he wrote a whole parser that does that whole thing. And you get to use it. You put a grammar, you write the native EBNF, sorry, that's the PEG syntax. You write the grammar in a kind of DSL syntax, and it generates the parser for you. And it actually scales, because you get from 1,000 lines of concise D grammar, you get to generate a parser that's 3,000 lines. So it's like a compressor, and it's much easier to maintain. So you can think of it as a highly integrated Lex and YAC. And now the last point I wanted to make is the work of Dmitry. So, our regular expressions. So in the D standard library, you get two kinds of regular expressions. One is like the classic regex, and the second is compile time regex, which takes the string during compilation and generates a specialized automaton exactly for that string, for that pattern. How much faster do you think it is? Compare these two. So this is like a generic automaton for all strings, and this is kind of a specialized for one particular regex. Which is faster? Sean, I see. Orders of magnitude. It can be a lot faster, of course, depending on the regex. And with this, I'm going to finish. RE2 is the main contender. And I'm actually using old results here because Dimitri just sent me literally like last night. He sent me an email. He said, I'm beating everybody. I'm beating everybody. So the decompile time engine is the blue. And right now it's kind of a parity with RE2. But actually with Dimitri's latest work, which is not committed, so I didn't show it, it's actually the fastest possible. I'm talking about parsing URLs, emails, and dates, the typical benchmarks for regex. So with this, we actually get to JIT that regular expression for dates, for example, or for URLs, into a very specific piece of code that's going to know exactly that pattern. And with this, you actually get results that are better than the best in the world in a very highly competitive area. With this, I'm done. Thank you very much. You've been great. Thank you. Thanks.